Hey, Fix listeners. I want to take a minute to give you all an update on our DPO, Smile Now Dental Group. In case you haven't heard, we've been opening up locations all across the country for doctors just like yourselves. We started several offices this year to show proof of concept, and it's been off to the races ever since. So, if you're looking for an equitable partnership opportunity where you can have a profitable business that supports you doing full arch, I'd love to hear from you. We're looking to add several locations in the next year and want to offer the training and support necessary to make one of those yours. If you'd like to learn more, you can go ahead and hit me up on Instagram at Dr. Tyler J. Tolbert, or shoot me an email at tyler@smilenowdentalgroup.com and say hey. Now, without further ado, let's get back to the show. My name is Dr. Tyler Tolbert.
And I'm Dr. Soren Poppy,
And you're listening to the Fix Podcast.
your source for all things implant dentistry.
So you mentioned a little bit about digital technologies and the improvement that we've had in record taking. And a moment ago, we were getting into CAD design a little bit, and I did want to ask, excuse me. So we talked about the relative inexperience of a lot of designers that are out there.
Yeah.
What are some of the things that you see in terms of how arches are being designed that is more often going to lead to failure? Maybe it's getting overlooked by dentists, and they're getting the design back. It looks like teeth. It's screwed in. Cool. What are some of those like little nuances that should be looked out for that maybe we're uncovering from some of this finite element analysis? What are some of those things that people are getting wrong that are causing mechanical stresses?
Yeah. One is definitely stress concentrations and embrasures.
Okay.
Yeah. So and the other one is screw channels. So
Okay.
So
What about
where the screw channels are located, and then also the overall implant distribution. So where the platforms are and how well the prosthesis is supported. But I'd say that the number one thing, I'd say the takeaway here is definitely when you're dealing with a high stress area, you really have two options in CAD software. You can add material to kind of reinforce it,
Sure.
or you can smooth the material. So embrasures, high pinch points, that's where stress, that's where all those tensor fields are going to like that.
Right.
That's where all
Sharp
that
edges.
stress is going to concentrate in those areas.
Okay.
And so
Okay.
crack initiation and propagation will occur at some of these really high pinch points.
Okay. So when you mention those embrasures, are you specifically talking about the embrasures between teeth or embrasures elsewhere in the design?
Yeah, so embrasures, occlusal embrasures, lingual embrasures, and facial embrasures.
Okay.
And-
Okay. So in areas where that's a little bit too sharp, we have a concentration of stresses, and that's where a crack can start, and then it can propagate throughout the entire restoration.
So and it depends on where the prosthesis is loaded, and so it's hard to guess where that's going to be. But generally, like I know on my designs, I typically on the lingual and occlusal embrasures, I tend to smooth those out more, and so that's they're less noticeable.
That's good. Okay.
Yeah, and then on the screw channel side,
Yes.
we're finding that obviously you want to have the smallest access hole as possible. Ideally it'd be magic, right? They just magically stay on, but we need screws, right? Prosthetic screws are quite simple. They have one job to do. And I don't know if you heard in the Q&A session, but basically prosthetic screws have one job, and it should be explained pretty simply because that's what they do. They're meant to torque. They screw down and they fasten the prosthesis to the platform of the multi-unit equipment. And their job is to maintain a certain clamping force for as long as possible. And the second job that they have is to essentially not overstress, especially like a ceramic or a polymer. So their job is to get as much clamping force as possible within the limits of being able to, without deforming the screw. So you're you're supposed to clamp it down with as much clamping force as possible and put as least stress on the material as you can. And so the goal is to maintain that until the next, at least until the next recall cycle. So I want people to understand that too, is that everything fatigues, right? There's movement and micromotion in all of our prostheses, because the human mouth is a fatigue machine, basically.
Yeah.
Constantly.
It's meant to. Yeah.
Going back and forth. So these prostheses and screws are cyclic loaded, all the time. And so the goal with a fixed prosthesis is to get it to at least the recall without any complications.
Yeah.
And in your recall exam, I would recommend that you validate the torque, that it's maintained sufficient torque.
Okay. And that doesn't necessarily involve replacing the screw. You can just do a torque test on the screw.
You can. I have I think I go back and forth on this, because it does get a little complicated there as far as how much actual stress is on the screw shaft itself. So you can plastically deform them, and then you're done. You know what I mean? So I would probably do a 2 to 3 strikes rule. Like, if it's not sufficient torque, you retorque it, and then essentially, if you find it loose, that if it's kind of not to spec, you might want to replace it at that point, or you could do it one more time and then replace it. But I would replace the screws.
And you're talking about a separate recall appointment. So let's say they're coming in on do you recommend 6-month or yearly basis?
I see my patients annually.
Okay.
Yeah.
We do too.
Yeah,
right.
I do. Unless there's some that I don't, right. But the classic,
what's the protocol?
The ones that I'm not really concerned about, as far as 6 months, then a year, then I can space it out to a year.
Okay.
But I do take radiographs annually.
Of course. Always. Yeah. So in other words, you see them at the annual recall, you do the torque test, and let's say your torque wrench or whatever you're using doesn't break immediately. You feel it tighten a little bit. You should probably notate that you have tightened that screw in particular. And so that the next recall appointment, if that happens again, you're like, okay, that's 2 strikes. Next time we're going to replace the screw. Do I follow that?
Yeah.
Okay.
Yeah. Because the universe wants those screws to unwind.
Entropy again.
That's the basic, I think it's basically the second law of thermodynamics, right? The entropy is in this case, it's always going to tend towards more disorder. And so the screws, they will never tighten. They're not going to self-tighten. They're always going to loosen.
There's no negentropic screw out there right now.
Right. It's not going to happen. And so your assumption is, you always have to walk into a recall, is that the screws have been under cyclic loading and fatigue, and they are prone to that. You should assume that they're loosened.
Okay. Very good.
And
go ahead.
Yeah. So the key is really that, and understanding those parameters, that evolved to the Badger screw, the screw that we developed as basically as a side project. And I was like, hey, this is, a class 1 medical device. Let's go ahead and let's start with the problem first and define our performance requirements, which is, I think, the opposite of what has been done traditionally. And in engineering, this is like how you really do it. One is you define the problem and you establish your performance requirements, and then you iterate and design to those requirements. So that was that's the design process that we have, and that we take.
So we've opened up the can of worms that is prosthetic screws. You've done it now. So I was thinking in setting up for this interview, I was kind of thinking about how do dentists generally think about screws. So every couple months nowadays, a new screw comes out and people are talking about it, right? And so usually the things that people want to know about it are, does the screw come loose? Like what screw loosening is coming out? And usually that's one of the first marketable things about it. It's like, oh, this screw is never going to come loose, right? People want to know, you're right. People want to know how much angle correction can I do with it?
Yeah.
They want to know, if they're getting into, especially if they're doing some FP1 stuff, if they've got some design experience, they're worried about the size of the screw channel.
Yep.
Usually the end all be all is going to be price, right? So like, is that a pretty decent rundown? Are there things that are being, tragically overlooked? Like what should people really be thinking about when it comes to screws?
Well, I think there's like kind of ease of use and ease of manufacturing, features, right? I mean, those are very reasonable. But I think screw performance is basically not even talked about. Like there's no, right? There's no like we know exactly, how we have a very, very good idea of what kind of clamping force our screw generates. We also know how much stress it generates. And we also have the smallest access or screw channel on the market. And those are basic parameters that I think are as far as performance parameters, those are very key. The other thing I would say about angle correction is ideally you want to, on the surgical side, you really want to focus your attention on implant timing and MUA selection.
Always, yeah.
Always. If you can avoid angled screw channels, you should. I mean, that would be the ultimate goal. Is to make things less on the manufacturing side. It's so much easier just to machine don't rely on angle correction as your fudge factor,
and so the main reason for that being that when you have an angle screw channel, that creates some manufacturing errors and workarounds that need to happen that can cause some structural integrity or something else.
Yeah. I mean, generally you have to remove more material. There's no question about that. And also it's, and that is going to increase stress or potential for crack initiation and propagation because of stress concentrations.
Okay.
Yeah, and so it's just you put a big hole in it basically.
Yeah, fair enough.
Yeah. And so you do want to minimize that, and sometimes you have to angle correct. I mean, if I do what I do currently is if I do have a certain abutment that I absolutely need to angle correct, I usually use a tie base. I usually use like an angle corrected tie base. It's much easier I'm removing a lot of material, and it's not ideal, but I can machine those we can machine those pretty precisely. But it's
like a custom angle corrected type base.
It does kind of add some. I mean, it's not ideal. So really, what we shoot for is in the surgery, really shoot for that. Implant timing, MUA selection.
Yeah, that's something we stress a lot when we talk about surgical nuances and stuff, and it's something I've spent more time on over time.
Yeah, I teach with Simon O and Juan Gonzalez, and that is what I see very consistently from really good surgeons is they have it nailed. Awesome. They're really good at understanding how to place multi-unit abutments and how to time the implants correctly.
Yeah. Right now, the thing that makes me most proud from a surgery, it's not torque values. It's not my surgery time. It's just access holes and straight on. Like that's pretty much the only thing I want to show in my Instagram post now.
Yeah. And I go to all my surgeries, and basically it's a team effort. I'm there to make sure that I'm getting what I want, what my goals are for the outcome of the surgery.
Hey guys, I just want to take a beat to talk about one of our sponsors, SIN360, specifically their full arch digital workflow. Here at the Fix Podcast, we've been using SIN for about 2 years, and one of our favorite integrations from this workflow is the Micron Mapper. Photogrammetry is an absolutely pivotal technology that has changed the way full arch is being done. It's allowing us to capture implant scans in under 5 seconds with micron level accuracy that's beating any type of scannable verification jig or analog verification jig, what have you, and it's able to do it in under 5 seconds. And guys, SIN360 is absolutely giving this thing away right now for $699 a month for 39 months with 0% financing. Think about that, $699 per month. That's about the cost of an analog conversion or fabricating an analog verification jig, or maybe even just a scannable verification jig. So I highly, highly, highly recommend you try this out. It's one of the most pivotal investments that you can make in a full arch digitally capable practice. To learn more, visit sin360.us/thefixpodcast and get yourself a Micron Mapper today.
Yeah. And something I wanted to throw your way, I actually saw it today, and I definitely want to come back to screws because I have more questions for that. But there is a product coming out, I won't say it by name, but I've kind of thought about this concept before. Definitely not far enough to ever make a patent or something like that. But now that this product's out here, so there's a continuously variable multi-unit, right? That kind of has like a ball joint on it, and you can sort of unscrew it, pick whatever angle you want. It's infinite degrees of freedom, and then you can screw it back down.
Yeah.
Do you see any issues with that biomechanically? Just off the top of your head, do you think that something like that could work well?
Yeah, I mean, I think what needs to for any kind of thing like that, like we definitely need fatigue analysis, like cyclic loading and fatigue testing on the stability. And then also the on the digital side, I think that you certainly could set an angle, and if you're doing photogrammetry data, I think that would it should work well, and hopefully that is quite stable. Then you should be able to design to that, and it could work. But I think mechanical, like it does need validation. It needs
right. You have to put it up to that kind of scrutiny for sure.
Right, because if it's not stable, then we're adding more mechanical, chaos into the system. So I would be. I mean, it could work well. I think it just needs to be validated.
Yeah, it can make our jobs a lot easier if it works, right?
Yeah, I mean, it could work well. I think that you could also get great results with implant timing and MUA.
Oh, totally. Yeah, no question about it. Yeah, that's still a fundamental skill for sure. But yeah, so back to prosthetic screws. So you talked in your presentation a lot about screw performance and how that's quantified and the different things that you actually measure. And I actually thought that was really interesting. So you've mentioned clamping force a few times.
Yeah.
Can you kind of speak to what that really is, how you measure it, how, let's say, your screw stacks up against other screws? What's like, I guess I should ask too, like, what is one of the most important things that we should be looking at when analyzing screws? Like, what's the data that matters a lot?
Yeah, I'm so one is we need, depending on how much load or force that the patient is applying, we need to make sure that the preload or clamping force.
Okay, so that's the same thing.
That's applied is sufficient to maintain stability of the bolted joint. So clamping force is a pretty big important number to know.
Okay.
And then on the other parameter, especially on provisional on provisionals that are usually like some sort of polymer, right? This 3D printed or milled PMMA. Right. We also want to look at how much stress that's applying on the material. And so these polymers can deform, right? They can actually yield. And so we want to try to minimize the stress on those polymers, and also ceramics too. I mean, zirconia is a very, very tough material. It's a very strong material. And so you might get away with more on zirconia than you would provisionals, but in general, that's what you're looking for.
Okay.
The other parameters could be access hole. So like
Mm-hmm.
for certain like FP1s, access
Yeah.
hole is going to be more important than like a giant, huge, zygo case with
Right.
it's got massive amounts of material.
Yeah.
So, but for our, as we kind of get into that, like FP, like small profile prosthesis, kind of like small FP3s to FP1 type of treatments, or
Mm-hmm.
FP2s, which in reality most of them are.
Mm-hmm. Yeah.
Then I think access hold probably would also be a parameter to look at.
Okay.
And then an angle, I think an angle correction solution it would also be a good feature to have too. I think
Okay.
it's not like I said, it's a, to call it a feature is, it's not an anti-feature, but it's not ideal. It's kind of a
Right.
bailout feature.
I see. Okay.
Yeah.
That makes sense.
So
Yeah.
the Badger screw is not angle corrected because we wanted to
Okay.
first start with that.
Okay.
We do have a honey badger that's coming out. So
That just doesn't give a shit, huh?
yeah, so that one is it's in development now,
Cool.
and so we'll be launching that one fairly soon too. But that's
Awesome.
that's a unique it is a unique challenge to kind of
Mm-hmm.
but I think we'll have a really good solution.
So what are some of so if we just talk about the Badger screw for now, what are some of the design, nuances that have really optimized its clamping force and the screw channel access?
Yeah, so it has a basically a concave profile, and through a bunch of iterations, we ended up with that profile through just basically computer aided engineering. So through this process of knowing what kind of design parameters we wanted to our performance goals we wanted to achieve, that was the kind of the fruits of that. So instead of like, hey, I've got a great idea for a screw, this is what it kind of looks like and stuff, we didn't do that. We started with like, okay, here's the problem. There's a big difference in this, in that approach. And so that, I think that's what makes great clever engineers so powerful, and so that's, we have a concave profile, and it is centering by nature, which is actually a good thing, because what I do is usually I always have at least 3 centering screws in my designs. So I'll usually place an anterior screw first. I used to, when I was doing these like early on, I would like put screws in and try to retain them and then shove it up in there and then start screwing it down. I do not do that. And I wouldn't recommend that. So what I do is I put a centering screw in first, usually in the anterior, and then I evaluate. I look for how much displacement we're off, like in a zirconia prosthesis. So I look for, you want to see a bullseye right into the threads of the MUA. So I evaluate that because I'm looking for distortions.
It's kind of like a Sheffield test a little bit.
It is, and passivity is very, very challenging to judge clinically.
Okay. Absolutely.
It's very hard. Right.
So when you use the term centering, are you referring to the centering of like the screw hole itself onto the multi-unit channel?
Yeah.
Okay.
Yeah. Okay. So the nature of the screw head, as you clamp it down, causes the prosthesis to center on where the threads, on the axis of the multi-unit, or at least on the axis of the threads. So it causes it to center, right?
Okay.
And then if those look like, if I'm seeing bullseyes, then we go posterior with centering screws. And then if I have like a tie base or basically like a flat ended screw that has more play in it, then I'll seat those, because I know that the prosthesis is
it's seated.
it's centered. And so and what I do is I don't tighten them, right? You snug. So it's kind of like a 5 Newton type of 5 Newton centimeter type of torque. So and so that the prosthesis is at least centered. And then we start slowly, in a star pattern, start slowly getting to our torque spec.
Okay, yeah, because I've definitely had situations. I've used a fair number of screws, I guess.
Yeah.
Where I'm usually putting in the anterior first, just because it's generally the easiest. And then sometimes you'll get that snug feeling, and then you go trying to screw in something else, and like it's just completely off base, like it's just not hitting. Or maybe you get a couple more in, then one of them just won't go, so you have to loosen up the other guys, and you get this one tight, and you're just kind of chasing your tail trying to get the whole thing to screw in. And you're probably introducing stress into the situation, especially if it's surgical type.
Yeah, and that's somewhat diagnostic, right? I mean, basically, hey, there's, this is not passive.
I'm fudging,
right?
Yeah. I'm bending the restoration to screw it in at this point. Yeah,
yeah, and so it's so that's that's a diagnostic, that's an indication that, hey, usually, if I do find that, I will often go back to the manufacturing part and find root cause, like where's the error here. But a lot of times, I don't. A lot of times, what I'll do is I will tighten it down, and hopefully everything seats. But I know that we're gonna have to redo this. It's gonna be a problem. But there's an art to seating. Like there is there's an art to seating. What you don't want to do is take a flat screw and just screw it down as tight as you can, and then start forcing everything else. You have to be systematic. But that's what I found that it seems to work well is I have a centering screw, at least in the anterior and in the posterior, and then I can at least get it lined up.
Yeah. Okay. Yeah, that's very good. Very good. And as far as so I'm curious about, different screws that will come out, they always have some torque value associated with them. Some of them you torque to 10, others 15, others 20. Is a screw that can tolerate a higher torque value when you screw it in, is that inherently better? Are you going to have better clamping force from that?
No.
Okay.
So it absolutely depends. When you torque, when you have a torque wrench and you torque to 15 Newton centimeters or 20, what does that actually mean? Right. So, right.
I don't know. I don't know what it means.
So what you have to do is you've got to break it down into the components. So this is kind of classical mechanics type of stuff, Newton stuff. So when you want to, when you have a force, or in this case, it's a rotational force, it's a torque, we're going to break it down into the 3 components. So one is you've got friction associated with the screw head, the bearing surface friction. And then you have preload. That's the actual resistance to stretching, right? And then you also have thread friction. You have friction on the threads, and so the way to break this down is that thread friction is about 5 to 10% because it's lubricated almost all the time. It's never dry. It's lubricated. So you can account for maybe 5 to 10% of friction from that. So we can kind of ignore that. So the biggest one is the screw head design, the contact patch, which is the bearing surface, and then the stretch of the preload. The preload is what we want. So you can so basically that contact patch, the resistance is going to steal a rob from preload. So the friction is going to take away from you stretching the screw. If there was no friction, then it would all be screw stretch. If there's no friction in the system, it would be all screw stretch. So 15 Newton centimeters for one screw is screw will get a certain amount of preload, and then for another screw it would be a totally different preload.
Yeah, so I usually think in terms of extremes to simplify a concept. So, if I
Yeah.
torque this to 20, that might just be telling me that there's a ton of friction
Yeah.
between like the screw interface and the material. It doesn't really tell me anything about how that screw has actually been stressed and preloaded.
Yeah.
Right.
Yeah.
Okay, got it.
Yeah, if you have a screw that has a
It's a big
high
flat.
amount of
Yeah,
friction on it,
yeah.
your clamping force might be too low to maintain
Mm,
stability.
okay, okay.
Yeah.
Interesting.
And so
Yeah,
that's why you really got to know what that stress is. And that's why you got, because stress is basically force on that and the amount of area that's on that contact patch or the bearing surface. And
okay.
then that's why you really got to know clamping force, like what it actually
Yeah,
generates, and how
yeah, because
you can mechanically test that with like a load cell. So you basically screw the screw down to spec, and then you see how much force is generated
okay.
on the material. So there are ways to validate that.
Right, right. Okay, that makes sense. So really the torque in and of itself, I mean, that's almost like I mean, it's rotational, and all we really care about is the direct vertical force of the screw onto the material, because that's what actually keeps it in the
Yeah.
mouth. The rotational force
Yeah.
is kind of irrelevant.
And think of preload or clamping forces like a shock absorber, right?
Hmm. Yeah.
It's constantly pulling down on this thing so that it can handle and resist all these
Yes.
like the chewing and rubbing, whatever the hell they're doing, like like basically it's like a shock absorber. And when that starts to deplete, when they start unwinding, then you get micro movement of the prosthesis, you get work
Hmm.
hardening or crack initiation in the
Hmm.
screw
Hmm.
itself, wear
Hmm.
on
Yeah.
the platform, all these little things that occur when clamping force is reduced by
Doesn't
half.
happen.
In fact, if clamping
Okay.
force is reduced by half, the screw's unwinding.
Okay. Yeah, that makes
Yeah.
sense. That makes sense. So is that to say that the more clamping force, the merrier? Or is it more so, maybe the degree by which the clamping force is reduced over time that's more important?
Yeah. That is so the more the clamping force, the merrier.
Hmm.
Is I think theoretically, yes,
Okay.
you want to maximize clamping force, um, and I think that is important,
Hmm.
but it's definitely more at what cost
Mm.
are you getting that for?
Yeah.
Because we can,
Right.
we can really we can reduce that bearing surface friction to a very teeny little contact patch, but
Hmm.
the consequence of that is super high stress, and
Ah,
we
yeah.
might be
Okay.
fracturing and yielding and
Yes.
deforming our
Okay.
material.
Yeah, so there's definitely a balance there, because if I put too much clamping force in a small area because
Mhm.
I've tried to reduce that friction to
Right.
increase the preload, now I've created a whole nother issue of actually like fracturing material, causing crack propagation and stuff. Okay, this makes sense.
Yeah.
Okay, nice, very
Yeah.
nice.
I
Yeah,
hope that, I mean, it's not that it's kind of complicated, but not too complicated,
yeah.
Yeah.
Right, right. Yeah, I mean it's more complex than I screw it into a high number and that means it's going to stay.
Right.
You know, and
Definitely.
that's kind of how I thought about it for probably most of my career. I think I
Right.
think I
Yeah.
very
Me
recently
too.
started thinking more
Yeah.
about it. Yeah.
Yeah, I
Yeah,
mean, yeah, I
definitely.
mean, honestly, our job is clinical. We're not, we don't think about, the a lot of the mechanical stuff behind these things.
Yeah,
And it's that's, you know, I mean, that's why we have engineers, right?
for sure. Yeah, absolutely.
I mean, our airplanes fly, our cars get us from A to B, and
Yeah,
there's a lot of
yeah,
expertise that goes behind
yeah.
that.
And those are considerably more complex than our restorations, I would assume. So,
I don't know, man.
well, maybe not. Who am I telling?
There are so many unknowns that we have
Yeah,
in our that it's actually very, very complicated. I would
yeah.
say it's tantalizing for an engineer. Like it's
Good.
complicated enough. We're not making
Yeah.
engine mount brackets. We're, or
Hmm.
something like that. We are our problems are actually, it's way more complicated than most than we would realize.
So I'm curious, you talk about a lot of the testing that you guys are doing throughout your various design interfaces.
Mm-hmm.
Have you been testing like other screws, other materials and things like that, and kind of seeing how competitors stack up? Like, have there been some surprises and like design nuances that people get excited about, but maybe, when you actually do the testing?
Yeah. So mechanical testing is it's quite expensive to do it. And maybe that's one reason why we don't have a lot of data in it. But most of our testing has been computationally. So we definitely know what the performance of the competitors, at least from an analytical point of view. But unfortunately, there's not a lot of studies out there. There's not a lot of like academic research on this. So we're, we haven't really. I think it would at some point we'll probably do more rigorous mechanical testing.
Mm-hmm.
But I think right now we're just kind of really focused on our screw and making sure that we have the best screw on the market as performance wise.
Great. So, as far as indications for the Badger screw, what is it useful in? I mean, I heard, FP3, obviously we've been talking about that. Is it great for all materials, or are there certain limitations of it, or is it a universal thing?
I think, we have not really optimized it. I would say it's for titanium. I don't know. We haven't really. It's not the point we haven't optimized it specifically for titanium. We have really optimized it for polymers and ceramics. Like that's really kind of what's our focus on that.
Yeah, and being that there's like a small screw channel access, I would assume that's great for FP1 and different applications as well. Okay, yeah, fantastic, and that's available now, and people can look up the Badger screw and give it a shot. Or?
Yeah, so we should by the mid-March, like early March, we're on pre-order status, and so what we have now is the latest updates that we have is that we should be shipping in. I think mid-March is when we're doing a nice anodizing process too, and so they're made. And the other thing that I thought was really important, they're made in America. So
there we go. Well, coming out of Montana, it has to be.
Yeah, man. I was like, we got to do this. Like, let's make these in America. Let's have our. We have awesome, machine, like basically industrial machine shops that have, we vetted with great ISO standards. As far as like all the stuff that all the boxes that we want to check, our tolerances are amazing. I'm really impressed with the manufacturing. Sorry.
Yeah, that's a whole nother aspect to choosing screws and really even implants as well, is that we don't even really think about is where are these things getting made, how are they getting made, to what standard are they being made. I barely ever hear anybody even speak to that, when they talk about different products and options that are out there. So that's good that you've gone through that type of rigor to figure that out.
Yeah. It's very important. The FDA, they do have to, like, if you make an implant or an abutment or something like that, there are ISO standards that have to be made in order to get it cleared. But
cool.
But for our screw, we're super happy.
That's awesome. Well, I congratulate you on innovating there, and I definitely feel like you were, kind of taking the industry to task to practice some things that we see in the automotive industry and aerospace, and hold ourselves to a higher standard, and kind of catch up with the times in other industries, because it's long overdue. Full arch is becoming so incredibly ubiquitous, and everybody and their cousins trying to do it, and if we're not holding ourselves to that high of a standard, we're going to see a lot of problems coming down the line. So
these go in patients' mouths,
these are people. Yeah.
We really, I think that, I think the industry in general, like is going to get way more sophisticated. Like it should. and I think it will,
Yeah.
So, and it's going to be for the benefit of the patients. It's going to be the benefit of the clinicians, and on the laboratory side too. I mean, everybody, with more sophisticated tools and advancements, we can definitely make this very costly and risky surgery and risky treatment. I think we can make it better. I mean, and we should be, the gold standard as far as in medicine. Like our stuff. Hey guys, our stuff lasts like 20 years.
Yeah, that's true.
I mean, so I that's our goal. That's our mission.
Very good. Very good. So to speak to your goals, your missions with Smart Tech, with your lab, with your office, like what are your biggest professional goals and ways that you are looking to impact Full Arch beyond what we've already talked about?
I think I love clinical work. I mean, I love being a clinician. I think I'll always do it, and
awesome.
and so. I think that's never going to go away, but I do. I think I'm most. I love working with my team of engineers, and I have like 3 jobs. It feels like, but I'm always working. So, but I really do love the innovation side of things. So I'll probably definitely continue with leading teams of engineers for innovation, and
that's awesome.
And I think I have that. I think what's very helpful for them is that I can live in both worlds. So I understand a lot of the technical things that they work with, but I also have that clinical insight as well.
Yeah. We need people that can be that bridge for sure.
Yeah.
And, hopefully we'll be looking at a future in the very near future where, we look at all of our restorations and we know where their stress points are. We can, assign that to every patient and know where their stress points are. We can create a model for, mitigating disaster long-term and make our work last a long time. And, there's downstream effects of that where the end user is the dentist, the lab, the patient, everybody benefits. And so I think you're really on a great path and you're influencing our field in a really strong way.
Well, thanks. Yeah.
Awesome.
Yeah.
So this would not be the Fixed Podcast if I didn't ask this question. So I do it for everybody. So what is your most controversial opinion in Full Arch dentistry?
Oh, my most controversial opinion.
Yeah.
Let's see here.
You got to upset somebody.
Right. I know. I think, well, I think we need to, I think where I'd like to see things improve is I feel like there's a lot of noise in the like on social media and things like that as far as marketing and KOLs and things like that, and it's and essentially we're kind of like I'd like to see more objectivity in the industry, and I do feel like we're manipulated too much, like we're basically there's a lot of manipulation going on, and I'd like to see a little more facts, like a little more like real rigorous facts and less like nonsense.
I think that's fantastic, and it shouldn't be a controversial opinion, but I think it is. And, I think we live in a social media era, right? And,
right.
Everyone is just trying to make noise for the sake of getting listened to. I play somewhat of a part in that, right? I have a podcast that I try to promote, and I want people to hear it. But I think for us, we want to bring that objectivity, and we're a sponsored show, and we talk to people about their products and their services.
That's
and everything,
fine.
But ultimately we do have to hold ourselves to a certain amount of rigor and show data and show, more than just a hand waving argument as to why something works and why other things don't. And I think that's really important. And, our mission here is just to help people make educated decisions. And I think, that should be a standard throughout the industry. So
I think it's just the nature of the industry right now. It's like how deals get done, how things are how things are progressed. Like if we didn't have that, we wouldn't be where we are today. But that doesn't mean that we can't improve or get better.
Yeah.
And so I think we put a lot of weight on like opinions, and I think we're going to get. I believe that those opinions are going to matter. Those people with high EQs, huge social networks, things like that, they are definitely going to always be an important player.
Yeah.
That is going to be important. But at the same time, I think we can manufacturers, innovators, their responsibility is to supply them with real, good,
data.
valid data. So that we can all, get to from A to B, in the right way. And so it just depends on the agenda, right?
Yeah.
So I don't know if that's that very controversial, because honestly, it's kind of like, it's a fact. That's just the way it is.
Yeah. I mean, it's the way it should be. And maybe instead of being a key opinion leader, we should try to be a key objectivity leader. We should we should bring data into the conversation.
I mean, it always comes down to opinion, but at the same time, I think that if we were talking about like a screw or something like that, right? Okay, like who's going to be a great opinion leader for a screw? Right? Is it going to be?
It's just the guy that screws the stuff in, right?
Right. I would honestly trust an engineer over. Like I would. That's who I would go to. That. Yeah. I would trust an engineer over somebody that just like uses them, on a daily basis. Like they may or may. I mean, because our opinions, like we aren't exactly the best witnesses of whether something is good or whether something is bad. It's just it goes back to like a happy patient isn't necessarily the best judge of how well you did.
Yeah. A 5-star Google review does not tell you how your screw performed.
No, it doesn't. And so I think we need to be a little more objective about how we assess things.
Yeah, no, I agree. And I think that, when we were talking at the symposium, you kept bringing up about standards in other industries, right? And it's like, we're inventing screws, and like there's all these new patents coming out with like different dental screws, different implants, all these things. But the screw in its form has existed for a very long time before modern dentistry ever existed, right? And there's people that have really put a lot of time and work and research into screw design. So there's a lot of things that can be learned that have already been discovered, and we don't need to reinvent the wheel. That was kind of a eureka moment for me, and I really appreciated that you're bringing that sort of context into dentistry and raising that standard.
Yeah, and I mean that's just one thing.
It's a small piece of it, yeah.
But there's so many, there's so many different things, and also, I think it's also really important to surround yourself with mentors, like as you go in your career. I think it's really critical to. There's a lot of bro science out there, right?
You bet, yeah.
I mean, there's a ton of it, right?
Yeah,
of course. And so like, I think as you move along in your career, I think you want to get those mentors that have more sophisticated models that you can learn from and feedback as you grow and learn. And I think like, we tend to like huddle in our own little groups and we stay there, and that's how you get stuck, right? And so I think it's really important to reach out to like a surgeon that like sews heads together, and like get those mentors that have a lot of different experiences than yourself, and right. And as soon as you feel comfortable in your group, it's time to move on.
I like that. No, that's
right?
good. That's good. And I think too is, I've always kind of, I can kind of tell the history of my own career through the people that I looked up to.
Right.
And I think that if you only look to the people that look how you want to look, right? The people that you're trying to model yourself after, that's not always the best way to go about it, because you need to kind of pick apart all the different components of what you want to be. Maybe you want to be clinically excellent. Maybe you want to be great in business. You want to be great in marketing. If you just model all of those things off that one person, you're going to be a little bit limited, right? You need to pick and choose from the people that do really well at all of those things, and then you can be a composite of those things, and that's what can make you, truly successful, because you're drawing from best practices of all of those things. Because no one is really the master of all trades. They're all jacks, right?
Yeah, I mean, and also specialize, like focus on what on you will be a master of none if you don't really dedicate your attention and focus onto a few things. And I think, at least for me, I'm happier if I really focus on a few things. Like, I don't do veneer. I'm not interested in cosmetic work. I love taking a hot mess and making it, and fixing it all.
That's awesome.
That's my focus. They have the biggest impact on patients' lives. And so I have tons of stories where patients have been totally changed, like their careers and everything, because they were a hot mess and we got them all straightened up. And so it's the most rewarding thing for me. But I'm not doing, I say no to a lot of things, and you have to get used to, if you want to, at some point, every dentist needs to say no. They need to learn how to do that.
Yeah, no, that's really good. That's really good. I think that's a great closing note for us, is, figuring out how to dive deep and become a master of something, right? Figure out what it is that you really want to go deep on and get really into it. And that's, that's something that inspired us to do this show, and it inspires us to bring people like yourself on it. And we're just so honored that you're able to spare your time.
Well, thanks. Yeah, no, it's been great. It's good conversations. I'm always up for that.
Awesome. Well, this episode will probably be airing right around the time that you're opening up distribution of the Badger Screw. So hopefully we can get that synchronized pretty good. And I'd just like to reiterate, thank you so much for bringing all your knowledge and expertise into this conversation. And, we look forward to continuing the conversation later.
Yeah, I hope it was helpful. I really do.
I'm certain it was. It helped me, if nothing else, but I think our audience is really going to like it.
Okay. Good deal, man.
Thanks, Ben.
All right. Take care.